Here's the list of the 5 properties of conductors in static equilibrium. I'm going to go over each one of these one by one, but before you take a quiz, you should make sure that you know all 5 and be able to explain why each one of the 5 is true. So here we have a uniform electric field and a conductor. This is a solid metal sphere. And remember, conductors, the key phrase is free electrons. What makes a conductor is it has free electrons. So if I take this conductor and I place it in an electric field, there's now electric field going through the conductor, and that can't happen. Why? What's going to happen? That's the first rule. So what happens is, because there's free electrons inside the conductor, a free electron in an electric field will be subject to a force. So what's the electron going to do? It's going to move opposite the direction of the field, right? An electron in a field moves opposite the direction of the field. And so what happens, just there's 4 field lines going through, 4 electrons are going to move over here to the surface. And those field lines will terminate on the surface. Of course, when the electron moves, that leaves behind 4 unpaired positive charges. So what are they going to do? They're going to move in the direction of the field. And they're going to go over here to the surface. And so, in effect, the 4 field lines will now come in, terminate on the surface, and then they'll continue. So outside the sphere, now can I erase these field lines? Let's try. I can't erase them, but what I should do is erase all these field lines. Let me redraw it. So the free electrons move such that the field inside becomes 0. 4 electrons move here, leaving 4 charges that move to the other surface. Now notice the way I draw it. I don't draw the charges inside because they can't be inside, right? Excess charge is always on the surface. If I draw them right on the surface, they're hard to see. So I'm putting them outside, but they're actually right on the surface, because the electron moves to the surface, and that's the point at which it can't move anymore. And so the field lines, the 4 field lines that pass through the conductor, those charges immediately move, and these 4 field lines terminate on negative charges, and then they continue as if they pass through from the positive charges on the other side. And what we see is what we know. You place a conductor in an electric field, and it polarizes. So just to summarize, the first property is the electric field. I'm going to say it out in a long sentence. The electric field inside a conductor always has to be 0. If it weren't 0, otherwise free electrons would move. And if free electrons are moving inside the conductor, it's not in static equilibrium. Okay, let's go to the next one. The next one, the net charge inside has to be 0, is logically consistent. So supposing an electron moves and leaves behind a positive charge inside, if there's an unpaired positive charge left inside when those 4 electrons move to the surface, there would be an electric field. So an unpaired charge inside a conductor means there's an electric field, and if there's an electric field, charges move. So if there's an unpaired, unbalanced charge inside a conductor, the thing automatically can't be in equilibrium because it violates the first condition, and free electrons are going to move. Number 3 says excess charge always on the surface. So notice we started with a neutral can, and when we put it in a field, we see that the electrons move in such a way that 4 charges end on the surface, and those unpaired 4 charges also have to end on the surface. But supposing we have a conductor and we put a charge on it. So here's a conductor and I've charged it. I've put 6 charges on it. Well, we know we can't have excess charge inside a conductor. We know if there's charges in there, there's a field. So it's not going to be an equilibrium. Free electrons are going to move. And what's going to happen? The excess charge has to end up on the surface. That leaves no field inside. It leaves no net charge inside. Well, even apart from the rules of conductors in static equilibrium, we know this is going to happen because these positive charges are all repelling each other. And so they're going to move as far away from each other as they can. That means they'll go to the surface, and they can't keep going because it takes more energy to make them leap off the surface. Of course, if we charge it enough, a spark would fly and they'd go off. But generally, they're going to go to the surface, and in a symmetric situation, they're going to be pushing away from each other, and they're going to be pushing each other this way. So they'll not only distribute on the surface, but they'll distribute evenly spread across the surface. Now, if this isn't a perfect circle, we're going to see later that the charge distribution isn't necessarily going to be even at the surface. So if we put negative charge on here, the same thing is going to happen. So charge always has to be at the surface. Now, the way it will distribute is that the field lines coming from those charges have to be, this is number 4, perpendicular to the surface. And the explanation of this is a little more subtle. But supposing we had this, oh, the field line goes this way. Well, the problem with that is if the field line is not perpendicular to the surface, there's going to be a perpendicular and a parallel component. And if there's a parallel component, see if you can follow this, if there's a parallel component of the electric field along the surface, the charge is going to move. So it will move until the field is perpendicular to the surface, and that's the only direction it can't move in. So finally, we want to look at a surface that's not symmetric. So the best way to show number 5 is with the diagram. E tends to be, the electric field is going to tend to be stronger where curvature is greater. So you notice where the curvature is very sharp, there's a much more dense collection of charges. And then where the curvature is least sharp, there's much less density of charge. So charges tend to collect where curvature is sharp. So the curvature here is probably, of course, this is very sharp. This is a little more curvature. This is pretty little, and this is almost no curvature. So I don't know if I've drawn it perfectly right, but that's what happens. And a way of saying this, I wasn't able to write it with the typewriter, is that the electric field is proportional, inversely proportional to the radius of curvature. In other words, where the radius of curvature is very small, the field and the charge density will be very high. And remember, these field lines, if you were to draw the field lines, they would all be leaving perpendicular to the surface. And the kind of quick, maybe not so convincing explanation is where this is flat, the charges are able to push each other farther apart. But where there's curvature, they're not able to push each other so far apart. And the difference in the charge density and the field strength can be very dramatic. Okay, those are the 5 properties, and those are the diagrams and the explanations that go with them. That should help you prepare for both the assignment and the quiz.